In this example, we're going to use the software RStudio to calculate a matched pairs t-test. In this scenario, it says Blastobike, a bicycle manufacturer, claims their bike will increase speed and hence reduce route times for cyclists. A simple random sample of 5 competitive cyclists were asked to record their times on the same route while first riding a standard racing bicycle and then riding a Blastobike. So what that means is that we're dealing with paired data because there are 2 measurements for 1 cyclist. And now it says that we know that the population of route times is normally distributed. This is important because in order for us to do a T procedure, we need to either know that our population is normally distributed or we need to have a larger sample size. And so we have a pretty small sample size in this case, it's just 5. So we need to know that those distributions are normal. And lastly, we have then the time recorded in minutes. So that's what this is here. There's standard time. So for the first cyclist, 29.1 minutes was how fast they rode their bike on the standard racing bicycle for the route. And then for the Blastobike times, their time was 28.3 minutes when they were riding the Blastobike bicycle on the exact same route as before. So each one of these values is then paired on either the standard time, and that's paired with the Blastobike time. So cyclists want to know, does on average the Blastobike reduce cyclist route times? And so the way that we set up our hypothesis test is based on the way that we're going to subtract our values. So because this is paired, we're going to subtract the individual values to get a vector of differences. And the way that we subtract is important because that's how we're going to know what we should set up for our alternative hypothesis. So the null hypothesis for a matched pairs procedure is always going to be mu d equal to 0. And so this means that the difference of the averages is just 0, and there's really no difference between these 2 groups. I want to know if the route times are actually reduced. So what that means is if I subtract Blastobikes from standard times, if the Blastobike has smaller times, basically I have a reduced time, then that means my differences will be positive. And so if the overall average of the differences is positive, then that will give an indication that the Blastobike actually reduced cyclist route times. So that's why my alternative is one-sided, and it is an upper one-sided test. So mu d is greater than 0, and it's important that we make that distinction. So first I'm going to run these lines so I can run in my data. Then I'm going to take the differences, so standard times minus Blastobike times, and I find that my differences are 0.8, 1.4, 3.7, and 3.6, and 1.8. So far things are looking good for being able to reject the null because all these values are positive, which means that in each case, the route time was reduced. Now we are doing an alpha of 0.05, so that's our significance level. So let's go ahead and run that line. And then we're going to kind of do this by hand. So basically take the average of the differences, the standard deviation of the differences, and then calculate our test statistic. So let's first find d bar. This is the average of the differences. And in this case, that is 2.26. So on average, the route times was reduced by 2.26 minutes. And so once we get d bar, then let's get the standard deviation of the differences. So this is just the standard deviation of diff. This is equal to 1.32. So on average, the route times are reduced by 1.32. That's the variation. So that varies on average by 1.32 minutes. And lastly, if we want to calculate now the test statistic, we can set up d bar minus our mu d, the hypothesis for that, which is equal to 0. So d bar minus 0, our hypothesized claim, our SDD, so our standard deviation of the differences, divided by the square root of n. So that's the number of differences. This is going to give us standard error. So if we want to just look at what this value is equal to, it is 0.5895. So this is then our standard error. And so if we run this entire section, we get our t-test statistic, and our t-test stat is then equal to 3.833. So that is our test statistic. Now, if we want to find the p-value, we can use this command pt. So pt of the test stat, or the t-stat, of 4 degrees of freedom is going to give me the area that falls below our test statistic in a t distribution with 4 degrees of freedom. But the thing is that I don't want that area that falls below because I want to match it up with my alternative hypothesis up here. This says mu d is greater than 0. So I'm looking for an upper tail p-value. So I need to subtract this from 1. I find that the p-value is equal to 0.0092. So based on this p-value and our significance level of 0.05, we're going to reject the null hypothesis. And that's because our p-value is smaller than our significance level. This is a very small p-value actually. And so we could even say that there's convincing evidence that the Blastobike reduced times or that the average is greater than 0. Another way that we can do this hypothesis test is using the t.test command, where we do t.test of the differences. Our hypothesized claim is that mu is equal to 0, so the average is equal to 0. The alternative is going to be greater, and our significance level, our confidence level will be 0.95. So if we run this line, let's look at the console a little bit better. We can see that we have the exact same test statistic that we had by calculating this by hand. So 3.833262. And we have degrees of freedom of 4. Our p-value is then 0.009283. This is the same as what we got when we did it, by hand, or basically just using R as more like a calculator rather than using the t.test command. So this is really great because it gives us all the information that we need in order to make a decision. And again, the p-value is smaller than our significance level, so we're going to reject the null. This p-value is very small. It's in the convincing range. So what that means is that there's convincing evidence that the Blastobike actually reduced route times. And so the route times are actually faster on average than the standard bicycle times for the same cyclists. All right, so if we wanted to find a confidence interval, then we can see here that our confidence interval is from 1.0 to infinity. This is a one-sided confidence interval and doesn't have a lot of meaning because its upper bound is infinity. So if we want to get a confidence interval, we can basically just change or delete this alternative line in this, rerun this, and it basically just does the default, which is a two-sided test. So this gives me a two-sided test, which doesn't answer my question of interest, but does give me a confidence interval. So basically what this is saying is that the Blastobike reduced times on average by 0.623 minutes to 3.89 minutes. And so we could also convert this into minutes and seconds, and I think that would make more sense. So if we look at this confidence interval, we could say 0.62 times 60 and 3.89 times 60, or more like 3 minutes and then 0.89 times 60. So we could really say that it goes from 37 seconds, so the Blastobike reduced times by 37 seconds to 3 minutes and 53 seconds. So that's one way that we could write this with a little bit more of a practical application of the problem. All right, so hopefully this video helped you understand how you can use the one sample t-test command or use R as just a basic calculator to do a matched pairs t-test.